Well, hello there, ladies and gentlemen. How are you? How was the coffee and cocktail break? All good? Thank you for being here on time. It's highly appreciated. So it being 4:10 p.m., it's time for our next and ultimate final session on this answer stage during the 10th Infobip Shift conference. Thank you once again for being here. And if you shared anything, Infobip Shift was the hashtag and still is, and you still have time to brag and praise it. So our next session, or our next lecturer first, he has more than 15 years of experience in design and development of enterprise platforms and formidable track record in building and leading teams of engineers. He's specialized in design of service-oriented architecture, and during this lecture, he will illustrate how the volume of transactions today brought up the need to rethink how you build your apps. He will introduce the Reactive Manifesto, its key principles, and the fundamental problem it's trying to tackle. Ladies and gentlemen, Srdan Srepfler. The stage is yours.
Hi everyone, can you hear me? It's great, first of all, to see so many faces after a year sitting in front of our screens. Especially, I would say, great to see people out of pajamas for a while. So, can you see my screen? Yeah, great. My name is Srepfler. I am the VP of Engineering at Huddle Gaming. We are a company that is providing services in the iGaming industry, which is not games, but rather sports betting and let's say all things related to games of luck, so lotteries, slots, jackpots, and things like that. Now, why do we care about these technologies? Because we have a very interesting business. In essence, just like there is Black Friday, which hits companies like Amazon every once in a while, or Kylie Jenner, which tweets something and suddenly Shopify just goes down because people just go there and start shopping for things. In the sports betting industry, in essence, it's like that every Saturday, every Sunday. Everybody's playing, everybody's watching the games, everybody's placing bets. So, what happened? Let's go a little bit with history. If you try to develop a typical service, let's say 10 years ago, you would write a simple class where you have some external data sources, you would add some caches, then very slowly things would start to get complicated. You would have to add more threads to the listeners, more threads to the connection pools. You would start to see issues when you hit certain numbers. Why? In essence, when you write sequential code, you're relying on a lot of blocking code. So that means every time you get or add something to the cache, you're blocking the thread which is executing this code, as well as, let's say, performing even network operations, database access, and things like that. Even the cache itself, if the API is synchronous, it's going to block your code for a while. That thread is going to be in use. Now, the good thing is that we kind of got really good at optimizing these things, so you could relatively easily predict the traffic and the amount of load that you can take. So there is this little formula by little, which tells you if you have X amount of requests per second and these requests are lasting for X amount of time, you know more or less how many worker threads you need to actually perform these operations. Of course, like we can put a little bit more detail in this diagram where you can see the worker threads, the connection pools, the actual network TCP buffer. You can do some tricks. So the applications are starting to get more and more complex. We can add queues inside the applications. We can put more cache. We can put more threads. In essence, this was our jobs for the last 10 to 15 years. And very quickly people noticed, like, you can tweak things, you can hit maybe 10,000 connections, and you will start to see serious problems. it wasn't very fun. So what is the fundamental problem on Java? Threads are mapped one-to-one with the system threads. So that means you cannot really have too many of them. It's easy to write sequential code, but this is not very efficient for the hardware. Also, writing concurrent code is not easy, even though Java had one of the best concurrent libraries. And at the time, the abstraction for performing a asynchronous call, which resolves eventually, which was implemented by a class called future, did not compose. What does this mean? So if you nest future actions or future values which need to come in time, you were not able to express this and then do so-called flat map on a nested sequence of future calls. So what are we trying to do? We are trying to, in essence, we want to make sure that our apps continue working. Every lost transaction counts as a loss for a business. They must react to variable load conditions. That means that they have to scale, regardless if Caitlyn Jenner just posted something on Twitter. We have to be able to reply to varying amounts of load. So that means not only scaling up, but also scaling down. And as an enabler of all this, all the apps must react to inputs which are message-driven. Message-driven is the enabler for all of this. And there are also two emerging properties. One is applications which are built in this principle, typically are more maintainable in time, and they're also more extensible. Like I can give you an example. We had an operation in a large bookmaker in the UK, where we were operating in Europe, and we had our own data feeds. And in one day we needed to launch in the US. And this meant completely different data provider, completely different data structure, and we needed to rewrite the whole thing. So what we did is we took a piece of the app, we switched just the modules inside this huge application, and everything just continued to work as nothing had happened. Because the whole system, if it's message-driven, it only changes its state based on these messages. There is no shared global state or things which create friction in your maintenance lifecycle. It's a, let's say, huge architectural advantage to develop systems like this. Not only this, in terms of extensibility, like if you're a business, you want to support always more and more business use cases. If you are not message-driven, that typically means that if your business has new scenarios, it's very difficult to actually go back on the drawing board and implement this new scenario without a lot of development. So what is reactive programming? In essence, it's a paradigm where we are not explicitly, let's say, doing things, but we are reacting on the data assets coming into the system. In a way, we are doing streams or lazy computation. Typically, this is event-driven, so different languages or different libraries or frameworks do it a little bit differently. For example, even JavaScript in a way is a reactive language because it supports event listeners, but this leads to typically so-called callback head. But as a principle, JavaScript and Node, for example, was one of the first application servers which managed to kind of capture this idea of the event loop, which meant that as long as you're not blocking that event loop, you can process a huge amount of requests per second and not really feel that much of stress in the system. Some people will say that this produces also clean and maintainable code. It really depends on the, let's say, style and how you're writing your reactive code. There are pros and cons to, let's say, all things. So let's go and see how the frameworks are doing it, if they're doing it with messages. One of these frameworks is called Akka. and it implements something called the actor model, where we are making the active part of the computation on something called an actor, which is an abstract concept. It's not really tied to a thread. By definition, so it's a concurrent primitive. There are many, it's not the only one, but it's very simple in its principle. So the only thing an actor can do is it can send a finite amount of messages to other actors, it can create new actors, and it can change the behavior of the actor based on the message. That is all you can do. So what does this mean? This means that, in essence, you have a Java class or Erlang class which has one method which captures a message when it comes through. It tries to pattern match on this object, and based on that, it executes some code. The code in this actor is typically sequential. All the state of this actor is local to the actor, and even though it's not a function, it's not a pure function, in kind of way it approximates the function. So this is the kind of the primitive that we want to use. Why? Because it will make our system more responsive, because you're not going to have 400 active threads on your machine. You can have many more, because these live on the heap. For example, to have 2.5 million actors, you need a gigabyte of heap, which is something that everybody has on your machines these days. You can have many more actors and threads. However, the same principle which we mentioned before with Node applies to this concept as well. You do not want to block the code that is executing on your actors. Why? Because they always execute on top of physical threads. So what does this mean? We need to add a little bit of logic here. So you have something called dispatchers. Dispatchers are the things which send these messages around. They go through typically something which is called the mailbox, which gets consumed by these actors one by one. Only one by one. And this is an advantage. Why? You can put some dispatchers and scale them in one way, and you can have another dispatcher which scales in another way. So that means you can put your database network operations, which take a long while because network operations are much slower than just normal computation, and they can run in a separate way. The early reactive frameworks like Vertex, for example, does not make this very explicit. But now it has improved in the latest version. But Akka had this concept for a long while. So keep your workload separate, and your system will be much more predictable and also much more tunable. And now we want to make systems resilient. How does Akka or the actor model deal with this resilience? There is this phrase, it's called, one actor is no actor. They always come in systems. What that means, when you're designing your application, you always have a tree. And this tree allows you to specify if something happens in your submodule, if you have an exception, say that this submodule is reading from Kafka, in one moment in time, this Kafka connection will break. So what does that mean? Should the application stop working? It shouldn't. The application should just change everything as it is, reload only the part of the system which we know that has thrown the exception, and restart it. There is an advantage to this, is that all your exception handling code is no longer in your code. So if you're used to catching your exception in your Java classes, you're not doing it there anymore, you're just throwing it. And that simplifies your code, if you're writing that kind of code. This is known as the let it crash principle. And it came from Erlang as a concept, which was one of the first languages which have adopted this computational model. And they were used by Ericsson in the telecommunication industry. So for example, they have actually measured this. You had systems which were running for 20 years without a single reboot or anything. And this is what they call 9 nines. Like in 20 years, they lost only 1 second of operational time. It's even more, let's say, advanced in certain terms from Java because you can change the code on runtime. You don't even have to shut down your system if you want to change the version of your code. What are you doing? Yeah. Also, I would like to say this one thing. There is the concept of location transparency. So when you are talking between actors, you're not really talking to an instance of an actor. You're talking through its reference. And this is something which enables that when actors talk to another actor, even if the second actor has crashed, the actor system will make sure it gets recovered, and it will eventually lead to the new instance of the actor. Elasticity. So no matter how much you can stretch these things, you will eventually have to kind of distribute your load on multiple machines. Now, there are many approaches to how you scale your systems. Akka has something which is called Akka cluster, which is a transparent way on how you execute actors on multiple machines. So you don't need load balancers, you don't need Kafka queues. If you want to do things in parallel, you can on multiple machines. It deals by itself to create the coherency between the nodes, so you know if a node crashes, that another node needs to recover the state of the actors on its own. It has some nifty tricks in order to kind of see is your network splitting, which it will eventually always split. And it doesn't need, for example, Zookeeper to actually run. The whole protocol is peer-to-peer based, so it's very simplified compared to, let's say, the existing Kafka, which needs Zookeeper to run in order to achieve this consensus. As you're running in a kind of multiple cluster, it's no longer, let's say, you want to have different kind of computational semantics. So the things which it comes out of the box is like you can have a cluster singleton, which means the actor is just one in the whole system. If the node with that actor crashes, it will appear somewhere else on the cluster, and everything's completely transparent. You can route between actors, where we have one actor which captures the messages and then routes to another set of actors. These messages can talk between them remotely. They can be serialized and sent over the wire with a high throughput UDP transport. You can do cluster sharding where you actually say, I want these nodes to be doing this thing, I want these nodes to be doing that thing. This helps with things like speed, like you don't want to send things over the wire if you don't have to. And you can also have like distributed publish subscribers, so that means you can subscribe to a channel and get notifications when something changes. Things have evolved a little bit as well. This, I would say, started with, like it always existed. Functional programming existed since the 70s. But what happened was that the first, let's say, commercial things started when Microsoft started to do the reactive extensions to .NET and JavaScript, actually. And what they did is they formalized this approach to streams. And it managed to simplify the way how they're writing code. All you need to do is do a handler for your next message, how to cancel the stream, or like what happens on an error, and that's it. And Akka also did the same thing. Why? Because at the time when you were writing Akka, like it still was before Java 1.8, the API was not easy to write. There was a lot of, let's say, also friction in terms of like productivity, which greatly was improved when they started to write Java-specific APIs. But still, like writing a pipeline, or in Java it would be a stream, computational stream of processing, turns out to be a very good fusion between the actors and let's say classical approach to programming. So what they did is that they wrote their own stream abstractions, which they call ACA streams, where you express your computation. But not only that, you can also pipe it to actual actors. So you have this fusion between actors, which have all the properties which we talked about before, and you have a DSL to efficiently and easily distribute these messages around your system. And then there was a whole ecosystem of integrations where you don't really care about that. Your source is a Kafka stream. Your source is an SQS stream, whichever. They have an implementation for everything. And you can make this arbitrarily complex. What you care about in 90% of the cases, what is the source and where you want to send it, which is the thing. The flow, typically, you have specialized flows which are very simple. Now, what is the future? There was this quote, like 1 month, 2 months ago. Brian Gatsby, the architect of Java, he said, I think Project Loom is going to kill reactive programming, which is a very interesting thing because, and it's true, because everything which we were trying to fix by now was because threads were mapping one-to-one with the operating system threads. But now that you are going to get virtual threads, that means creating a thread is really, really going to be cheap. So you can actually create 2.5 million threads. However, this does not solve all issues. You still need to coordinate, you still need to apply back pressure, which is a technique to say if you have a stream and you have slow consumer of messages, you need somehow to signal that you cannot cope with the low, slow down. So all these things continue to be a problem. Probably what we will see is there will be some sort of hybrid approach where streams plus virtual threads will be able to accommodate the scenarios which we were talking about. But not only this, we're going to see some other benefits as well. So typically debugging asynchronous code is really, really difficult. You don't see stack traces as they should. So you don't have a sequence, what went wrong and where. If you use virtual threads, you're actually leaning on the language to actually show you where things got wrong. And many more advantages. However, this is a good thing. Why? Remember when I said at the beginning, an actor, if you write like in a normal style, the code inside is really sequential. And that programming model will probably continue, let's say, to exist, regardless whether or not Java is reactive or not reactive. What is important in this talk, I would say, is try to think about the business problems of your company and try to make your applications to behave like this. Doesn't have to be ACA, it can be Vertex, it can be Node, it can be whatever. But always remember the principle. Your application needs to be responsive, it needs to be resilient, and it needs to be elastic to load. Maybe you will not have to use messages. However, there will likely always be a niche where this will be an enabler, because messages do one critical thing. They decouple things in time. And you always want that. And I would say one other thing which is coming, which is going to be really nice, is that even on a low level, the Linux kernel itself is going to implement an interface which implements you in a non-blocking fashion, similar to BSD, similar to Windows. Some references, and I will say here, thank you.
Thank you, Srdan. Thank you so very much. Good luck with all of your endeavors, be it private or business. And thank you, audience, of course, for staying till the end. in front of the answer stage. One thing I need to tell you is that you can actually stay here because we're going to move the curtains again. And the pizza slices are again going to connect each other, and we're going to have a 360 stage for the final lecture of this year's Infobip Shift Conference. So if you feel like it, just stay here, rest for a bit, and then it starts, and then at 5, it's the closing ceremony where you will get all the rest of the information. So guys, it was a pleasure to be here with you. Thank you so very much for your attention. Thank you so very much for being here and for supporting conferences such as these. We do hope that you got all the relevant information which is going to be good for you in your private, but especially in your business developing life. So good luck with everything and change the world, guys, and make some good money. Ta-da!